All right, guys, so this is our video on the graphs of logarithms. We're going to start by talking about logarithms as the graphical inverse of exponentials. But we're also going to talk about the graphs of logarithms and logarithmic functions in their own right. So right here, we're going to start by looking at the inverse functions. F of x equals 2 to the x, and f inverse of x equals log base 2 of x. So right here with our f of x, we can get some quick ordered pairs and sketch the graph of our function. If we plug in the x value of 0, we're raising 2 to the 0 power, and that is going to give us our initial value of 1. When we plug in 1, we're saying 2 to the 1 power, and that's going to give us the ordered pair 1, 2. And when we plug in 2, we're raising 2 to the second power, which gives us 2 squared as 4. And we get the ordered pair 2, 4. If we were to plug in the exponent of 3, we would say 2 to the third power is going to give us 8. And that would give us this ordered pair right here. And we're seeing that exponential growth as x goes out to positive infinity. When we raise 2 to negative powers, basically what we're doing is we're taking that 2 down to the denominator and multiplying it there. When we raise 2 to the negative 1, we're bringing this 2 into the denominator, and we're going to get the output of 1/2. When we plug in negative 2, we're taking 2 squared into the denominator, which gives us 1/4. And as we raise 2 to higher and higher negative powers, we're bringing it into the denominator and multiplying it by itself over and over again, which gives us smaller and smaller values that are closer and closer to 0. And that's where we see our horizontal asymptote of y equals 0 for that exponential function. We can sort of sketch the graph looking something like this. Now, when we're looking at the inverse, we could just sort of say that we know the inverse is going to switch all of the x and y values, right? Giving us the table that we're seeing right here. But in general, what I want us to do is take a second and really think about how we're getting these ordered pairs, right? Remember that the logarithm, log base 2, is going to take an x value and say, what do I have to raise 2 to in order to get that x value? That means that all of our outputs are, of course, going to be exponents, right? And we can plug in x values and think about what exponents we would have to raise 2 to in order to get those numbers. So right here, if we plug in 1/4, we're saying, what do we have to raise 2 to in order to get 1/4? And that is going to be the exponent of negative 2. If we plug in 1/2, we're saying, what do we have to raise 2 to in order to get 1/2? And that is going to be the exponent of negative 1. If we plug in 1, we're saying, what do we have to raise 2 to in order to get 1? And that is going to be the exponent of 0. If we plug in 2, we're saying, what do we have to raise 2 to in order to get 2? And that is going to be the exponent of 1. And if we plug in, rather, 4, we're going to say, what do we have to raise 2 to in order to get 4? And that is going to be the exponent of 2. And we're clearly seeing those ordered pairs reflected across that diagonal line, x equals y. Looking something like this. And right here, the other thing that we can say is that for inverse relationships, right, any behavior that we see along the x-axis for our function is going to be behavior we see along the y-axis for our inverse, which means that right here our horizontal asymptote for our exponential function is going to be a vertical asymptote for our logarithm. We're going to say we're going to get that vertical asymptote at x equals 0, and our logarithm is going to follow that vertical asymptote up from negative infinity and extend out over the positive x-axis as a reflection of that exponential function, right? So right here, what we're going to do is take a look at analyzing this logarithmic function. So right here we've got the graph of just our logarithmic function, and we want to talk about analyzing this guy. So right here we're going to look at the domain first. When we look at the domain, what we want to do is think about how we're evaluating these x values, right? So right here, any x value we plug in, obviously, we're saying, what do we have to raise 2 to in order to get that x? Now right here, what we're going to be able to see here is that there's nothing I can raise 2 to in order to get a negative number. So right here, if we're looking at y equals, or even let's say f of x equals log base 2 of x, if we want to evaluate log base 2 as a function by itself, there is nothing I can raise 2 to in order to get a negative number. So right here, log base 2 is not going to evaluate any negative x. Similarly, there's nothing I can raise 2 to in order to get 0. So right here, again, there is no way that log base 2 is going to be able to evaluate an x value of 0. And what we're seeing here is the last domain restriction, right? And that is that we can have no x value that gives negative or 0 in a log. So right here, that's the last domain restriction. We know we can't have any x value that gives us a negative under an even radical, and we know we can't have any x value that gives us a 0 in the denominator of a rational function. And our last domain restriction is that we can't have any x value that is going to give us a negative or a 0 within a logarithm. So that means that our domain for our logarithm is going to be from 0 to positive infinity, right? Now right here, when we're looking at the range, we can basically see that we're coming up from negative infinity with our vertical asymptote. And if we think about it, as we evaluate x values that go out to positive infinity, we're going to need exponents that go up to positive infinity in order to raise 2 to higher and higher powers to get those larger and larger outputs. So actually right here we can say that the range is going to be from negative infinity to positive infinity here. And we're going to see the graph of our logarithm slowly go up to positive infinity, right, as it extends out. Now right here, it doesn't look like that. It looks like it's flattening out, but actually we do go up to positive infinity with our function values, just very, very slowly. Right here we can say that the graph of our logarithm is increasing on its domain, decreasing nowhere. It is not bounded since we go up to positive infinity and down to negative infinity. We have no extrema. We have the asymptote, x equals 0, right? And right here, we're only going to have end behavior in one direction. So we're going to say that the limit of f of x as x goes to positive infinity is positive infinity, but we're not going to have any end behavior as x goes out to negative infinity since the graph of our logarithm can't evaluate any negative numbers. So right here, what I want you guys to do is to go ahead and evaluate the graph of the common log of x plus 1. Right here, you guys can go ahead and graph it and then evaluate the analysis right here. Remember that you can type this into your calculator since it's the common log. You could also think about it as a transformation of y equals the common log of x. In general, right here, we can say that just like all exponential functions with a base greater than 1 are basically going to look like that exponential growth, we can say all logarithms with a base greater than 1 are going to look pretty much the same too. So they're all going to look something like our log base 2. Right here, since the common log is a base of 10, we're going to be able to say that it's going to have basically that same shape. It's going to have a slightly sharper trajectory. It's going to hug the x-axis a little bit more, but it's going to look roughly the same in terms of the shape. And we can think about the common log of x, right, and then the transformation we would get from adding 1. So right here, why don't you guys pause the video and go ahead and give this analysis a shot. All right, so right here, if we type this down into the calculator, we might see a graph that sort of cuts off a little bit, but right here we want to know that we are going down into a vertical asymptote with the graph of our logarithm. And so right here we want to really be sure that we understand that this graph is going all the way down to negative infinity. What's happening with your calculator if you see it cut off anywhere going down into that vertical asymptote is that your pixels, we don't have enough pixels to sort of see how close it's getting to the x value of -1. But in general right here what we can say is adding 1 inside our logarithm is going to be a horizontal shift in the opposite direction. So we see the graph of the logarithm and the vertical asymptote shift to the left 1. That means that we've got the vertical asymptote now at -1. and our domain is from -1 to positive infinity. The range is going to be from negative infinity to positive infinity. We're going to be increasing in our domain just like before. Right here we're going to have the asymptote of x equals -1, and just like before we're not going to be able to extend out to negative infinity, so we've only got that end behavior extending in the positive direction here. And as x goes to positive infinity, we're saying our function values are going up to positive infinity, but they are doing that very, very slowly. All right, guys, so let's move on to the next page, and I'm going to have you guys do some quick work with transformations here. We've got the graphs of log of base 2, the natural log, and the common log, and we want to think about what's happening with these transformations. So basically what we're going to do is graph these transformations real quick. And I want you guys to give this a shot yourselves. You should be able to sort of reason with these transformations, and we'll come back and look at this in a second. All right, guys, so I've drawn the graphs of log base 2, the natural log, and the common log right below, and we're going to talk about these transformations. So right here, we're looking at 3 times log base 2 of x plus 2. So first we can talk about the x plus 2, which is going to be a horizontal shift in the opposite direction, taking us 2 to the left, which means that our vertical asymptote has gone from 0 to -2 now. The other thing that we're seeing here is a multiplication of 3, which is of course going to be a vertical stretch of 3, because that multiplication of 3 is happening outside the function, and we're seeing a graph that's going to look something like this, right? Right here, when we look at the natural log of negative x plus 2, in order to evaluate this transformation, the first thing we want to do is factor that negative off of the inside of our function. So we would say we've got the natural log of negative x minus 2, and that means that right here, first what we're seeing is a shift 2 in the positive direction. So we're basically going to see that vertical asymptote happen now at the x value positive 2, and then with that negative we are seeing a horizontal flip. So right here we can see this as a flip left to right rather, and we're going to see our graph looking something like that. Finally, right here with our r of x, we've got 3 minus the common log of x. So right here, first we can say that we are seeing a negative common log of x. We can think about this as negative common log of x plus 3. And right here, that means that we're flipping this guy upside down, right? Flipping him over the x-axis. And then right here, with that addition of 3, we're going to move him up 3. So he's going to go 3 units up. So right here, I can take my x-intercept and move him 3 units up to about there, and I would see the graph of 3 minus the common log of x looking something like that. All right. So this is our video, a little longer than I'd hoped, but we gotta cover this. So right here, we'll